So on page 128, you've got a formula, and it actually says I equals 1 to I equals n. This sigma thingy there is meaning sum, and it's the same button in your Excel spreadsheet that sums. We've got x times the probability that x equals x. Now in your book it says xi times the probability of xi, of that outcome. So I guess this here is a specific outcome, and this here is the random variable. Okay, so the random variable can take on certain specific outcomes. I'm going to show you this formula with a very simple case that you're all familiar with. Whoops, there we go. Okay, so we've got a dice. What are the possible outcomes for the dice? So I'm going to have x as my possible outcomes. So I've got a 6-sided dice. What are my possible outcomes? 1, 2, 3, 4, 5, and 6. Those are my possible outcomes. The probability that the random variable x, so that's when I throw the dice, what comes up, is going to be this outcome is, if it's a fair dice, 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. Is that okay? Yeah. What does this formula mean? This formula means I am going to think of that as x1, x2, x3, x4, x5, and x6. And I'm going to think of that as the probability of x1 happening, the probability of x2 happening, the probability of x3 happening, the probability of x4 happening, probability of x5 happening, and the probability of x6 happening. Hopefully you can make sense of what I've done there. This says sum them all up. So what it's actually meaning is you get that times that, plus 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 that times that. Okay? What does that all add up to? The expected value of x, yep. And what is it? Does anyone know? .5 is correct. I mean, what would your working look like? You would have the expected value of the random variable x equals 1 times a 6 plus 2 times a 6 plus 3 times a 6 plus 4 times a 6 plus 5 times a 6 plus 6 times a 6, which is 3.5. Now I'm going to show you that. So here I'm going to have 1, 2, 3, and here I'm going to go equals rand between 1 and 6. Hit return. And then I'm going to just copy that down. Okay? Now I'm going to grab those two, and down I'm going to go. She says hopefully. Keep going down. Down, down, down. This is going to be my way of throwing a dice lots and lots of times. Okay, I'm going to let go now. Alrighty, so here I've thrown a dice, cheats way, simulation way, which is also in the standard, and I've done that 752 times. I'm going to grab all of those times that I've thrown the dice, I'm going to add them up. I'm going to do sum. So notice that that thing, auto sum, has got that same symbol, auto sum. Okay, now it's big. Now how am I going to find the average outcome? Nice, so I get that and I divide by the number of times I threw it. And 3.42. Now let's have a look. Just just want to make that nice and big so you can see it. And every time I hit a key, it will do it again. What's happening? Yeah, what's the average? 3.5 is our theoretical average, right? What happens if we went like that and we went 1, 2, 3? I'm just going to actually just throw the dice 8 times. So here I'm going to go equals the 33 divided by the 8, okay? You watch that there as our average of that many times throwing the dice, okay? Compared to this one where we threw it how many times? 752. Okay. What do you notice? This one here, is it changing much? No. This one here? What's happening with this one? Bigger range, beautifully said, more variation. So the more times we throw the dice, the closer we are to the theoretical or expected value. Okay? So the expected value is when I throw a dice, if I threw it for billions of times and averaged it, I'd actually, my average would be 3.5. But you never get a 3.5 when you throw the dice. So that's our mean over a long time. It's our theoretical mean in a way. So you can see if you only do it a few times, it's got quite a big range, whereas you do it a lot, it's there. Okay? I'm going to show you the same thing I showed the other class. Okay, so for this standard and for all of the standards, there's quite a lot of stuff that you need to know, and this particular applet will keep coming back at us. So there's some language I'm going to throw at you. When I roll one dice once, I mean, that distribution doesn't look anything special, does it? Oh, wow, that was amazing. Okay, is it? What shape? I'm going to do this 10,000 times. What shape is that? A box. It's a uniform distribution. Uniform, okay? Right, now, 2 dice. If I do it just one at a time, I get this. Does that have much of a shape? Not really. What is the shape of the actual distribution of 2 dice? Is called, no, it's triangular. But if I go 3 dice, that's looking quite bell-shaped. And if I go 4 dice, it's even more bell-shaped. And 5 dice, nicely bell-shaped, yeah? Yeah. However, if I'm going to go back to 5 dice, and I'm going to just do 5 at a time, does that look like a normal distribution? No. But it's from a normal distribution. Okay? So it's not until I get a bigger sample size or do it more repetition that I actually am going to, that doesn't really look, it looks kind of maybe, but it's certainly not wonderfully normal. Whereas this is so normal, it's probably boring. Yeah? Now, the other big message today is that in theoretical probability, long run kind of probability type situations, if you do it enough times, a trillion times, it will then approach that mathematical perfection of the normal distribution. But in real life, the normal distribution is always an approximation, and it's always a guess. Does that make sense? So the normal distribution can be applied in probability land, and it can also be applied sort of statistical land. So when you're dealing with measurements and things like that, the height of everybody in the world might be normally distributed, but not perfectly so. Yeah? Because there's real things, real anomalies. You imagine there's going to be a limit to how tall a person can be, and a limit how short. There'll be outliers, there'll be all sorts of random things. Yeah? Just to think about. So we're looking at discrete random variables. Here's your formula sheet that you will be giving in the exam. And the point of this video was to show you this formula here is the one that we are making sure we know how to use today, and this will be the only chance you have to learn this. From here on in, you have to apply it. Okay, so it's this bit here, mean and variance of a discrete random variable. So this is the mean, the expected value of x is another thing for mean, and the formula is add up all the possible outcomes with their probabilities. So you get the outcome, times it by the probability, add them all up. One other thing, when you get these little boxes, so you have these kind of boxes where you've got the outcome here and the probability that the random variable x equals that outcome, okay? And you've got, in this case, I'm just going to copy what was in the book, 3, 4, 5, 6, so the possible outcomes, and the probability 0.4, 0.2, 0.3, and 0.1. One key thing is, what do all these probabilities have to add up to? 1. So they must add to 1. Okay? So how would we find out the expected value of this random variable? We'd go 3 times 0.4 plus 4 times 0.2 plus 5 times the probability of a 5 turning up plus 6 times the probability of a 6 turning up. And that's our mean if we did it a billion trillion times. Yeah? Cool? Done.